almost the magic time. Oh, it's the magic time. What do you think, Anna? Do you have the microphone? Yeah, do you want one? Yeah, it's like magic. Don't you smell it?
It's no coffee.
That's true. Oh, I got some.
I smell. Yeah.
So I just before we start and do the.
Yeah.
You do the thing first?
Do that first.
Yeah, it's just a little bit of midterm 2 statistics.
That's
so
right.
just wanted to show you a
We're
little
that
bit
good.
for those.
How?
So that was very interesting. So we found that on average, about 9.6 coughs were a minute. That was the rate throughout, and it was pretty consistent, which I thought was pretty interesting. And that means that on average, every 6 seconds there was a cough. If you think about the number of students in the class, on average, every one of you had 1.3 coughs throughout the exam, which I thought was pretty cool. But what was surprising to me is that when I timed the timing between coughs, so normally if you think about random processes, something that events like radioactive decay and things like that, they usually have a Poisson statistic, so Poisson distribution. You'll learn about that in CS70 and 126 and some other probability class. Then the statistics of the interval between those events is usually exponential. And I actually found that it was not really exponential. There was kind of like a little bit of a, it wasn't dropping exponentially like I was, hypothesizing it would be. And maybe it's only over 5 minutes, so it's not enough statistics, but I thought that was very cool. So yeah, so hopefully nobody gets sick.
All right.
Okay. And now, ready? Ready? Come on. What was that?
Ready?
Welcome, EECS16A. Woo! All right.
Great.
Going strong.
We have a lot of announcements.
Oh, we do? We do? Oh, yeah, we do. Tons of announcements.
We have a lot of announcements.
Ooh,
I
wow.
posted yesterday labs. What's happening to the labs, right? Clear? No labs this week. We will we'll postpone the Touch 3B, because we want you guys to do that in the lab with hands-on. So we will give you more information as we know how many resources we have available. But that lab is going to be running in the last week of the semester, after you come back from Thanksgiving, and during our week. Okay, but that's all posted. And we are going to release the last lab, APS lab, which you can do all on your own. We highly recommend that everyone does that lab, because that lab was designed to help you do well in the final, and everything that you're learning now on Module 3, you're going to put into practice there. So, tip for those who come to class, huh?
Yeah.
Really do that lab, okay? We said it's optional, but
Shouldn't be optional, really, because
shouldn't.
it's really your chance to understand what least squares, cross correlation, inner product is, and kind of like embed it in yourself, because you're doing all this kind of math stuff, but like actually doing stuff that's real, taking good signals, doing all the correlation, you'll see all the subtleties that you don't see so much, or maybe you didn't really absorb when doing it in just homework and class or discussion. So
Right.
really, I mean, if I were you, I would say not optional. I would say must do, and it's amazing.
Yeah.
It's
I mean,
amazing.
we had to compromise due to resources, but you guys should not compromise on your own understanding. So make an effort to complete that lab. Okay, regardless of grades, right? We are here to learn. So here's our advice. Okay, discussion. Discussion, we have been posting also on ad what discussions are available. We are making recordings available. We do have content. So we are still working on the development of the content for discussion, homework, and everything else that you need in the class. So no break on learning there. And so keep checking. Every Monday morning, you should know where you should go for a discussion or which Zoom link you can join in order to have your discussion. And same for Wednesday this week, this coming week, it will be a holiday. But same thing for when you come back from Thanksgiving. Homework, business as usual. Now, you have to be patient with us regarding the grading of the midterm.
Hot.
Yeah. The grading of midterm. We will do our best to grade as fast as possible. But, you know, when you walk around the campus, you know what's happening. And you saw how many people are here for the proctoring. So we are doing what we can with the resources we have without, of course, overworking the TAs who are helping us. And the 2 professors are definitely overworked, but it's okay. We are here for you guys. Then, what else are we going to do? Midterm 2 redo will be released. And that's important, especially if you want to take advantage of the clubber opportunity, right? So if you don't do midterm redo, you don't qualify for clubber for the final. But here's our present to you. Everyone can get 100% clubber if you do the midterm redo, okay? Questions, okay. And that's it. As far as announcements. Instead of 90%, you can get 100%, but you still have to do. If you don't do the redo, you don't qualify.
No redo, no clobber at all. Zero. Zero clobber.
If we didn't do the midterm 1 redo, do we get any clobber benefit out of doing the midterm 2 redo?
I don't.
Midterm 1 is long gone. If you didn't do the redo, then you're not entitled for the 90% clobber.
Right. For 1, yeah.
Can't hear.
Read.
Okay.
My answer is always read. It's there. Okay. That's it. So it's instead of 90%, it's 100. Everything else is the same. Okay? Questions? All right. Let's go to the important business, which is the learning. The stage is yours. My hair got caught in my glasses. Sorry. And I complained.
Nothing like a good smell of coffee in the morning. Anyway, all right, so yeah, good morning. I forgot to change that. I guess this is good afternoon.
Afternoon.
Good afternoon.
Oh, a mistake from the past.
That's a mistake from the past.
Oh.
Okay, we decided to teach the material that we supposed to post on Tuesday, but due to technical difficulties, we only posted yesterday. And then I thought, I don't know, we're going to come here. Some of you have watched it, some of you haven't, and I don't know what to do. So what we decided is we're going to teach the material that we said we're going to do on Tuesday now, and post the Thursday, today's lecture, the one extra one, online, so you can watch that one. And so for those of you who have watched, some of you have watched it already, you get to re-entertain, or you can, just go or do some other stuff. But there's not a lot of you, hopefully, because I was really freaked out that there might be like half-half, and it's just like embarrassing. So I don't know what to do. So we're going to talk about today about cross-correlation, which is actually extremely useful operation. Extremely useful. I mean, you do not know how useful that operation is. By the end of the day, you would know, and it's just used all over the place. So it's extremely important for detection, classification, which we're going to do today. So last time we talked about GPS and the idea of GPS, known position of these satellites. Each satellite has its own signature. They transmit all on the same channel. Shut up. And then, we want to find our position from the signals of these satellites. And first of all, we need to identify which satellite is transmitting. Then we need to figure out how long does the signal take from those satellites to us. And then from that, based on the speed of light, we can figure out those distances and try to solve for our position on this beautiful planet. Okay? So what we talked about last time is about inner product. Remember inner product? I did mention inner product when we did like this, like that. Ah, hurts. When we did like this and like that. I'm going to just do it slower. When we did a long time ago, matrix multiplication, Y transpose X or something like this, I told you, oh, this is an inner product, but like we'll just talk about in module 3, which we did, because it's module 3 right now. And so we talked about inner product, and what inner product does is measure the similarity between vectors. Super useful because vectors can be thought about as signals. And we want to find similarity between two signals. That is a good measure, the inner product between them. For example, you can think of my face and Anna's face as signals. Let's say you take a picture of us. You can compute an inner product on that two vectors, between those two vectors, and find how probably dissimilar we are, right, Anna?
Yes.
Yes.
But we both have warm hearts.
But maybe there's some interesting actors that you can do inner products between us and kind of find maybe good correlation. Probably, I don't know, whatever. Just keep going. All right, so we talked about inner product, and we talked about using that for classification. And what we're going to do today is we're going to look at basically computing delays with cross-correlation, which we don't even talk about, but cross-correlation will turn out to be a bunch of inner products. It all come down to a bunch of inner products. And then maybe we'll get to finding position with multilateration. So again, our moving example, running example is GPS. Satellites transmit, we receive. We try to find our distances from these satellites, and based on these, we can find our location. It's 24 satellites, known position, time synchronized, 8 usually visible. And the problem, again, I want to reiterate, classify which satellite is transmitting, estimate distances, and then estimate position from all those distances, which may not be consistent because of noise or some other interference. Okay? And the tools, inner product, which we covered, cross-correlation, which we're going to do today, and least squares, which we're going to talk about next week. Is there a class next week?
Yes.
There is a class on Tuesday.
Yes.
All right. So last time we talked about classification and using inner product as a classification, and we said, oh, we've got these vectors that we had the setup where we had two vectors that are being transmitted, either this one or this one. It was 1, 1 or 1 minus 1. And we measured some signal that came, and we asked, is this one closer to this, or is it closer to this? And we tried to then optimize, come up with an optimization that a computer could do it, because this is in R2, easy to find, but what if it's R3000, or R billion? Then it's like you can't really visualize it, right? So it's not as obvious. And so we define an error measure, which is the length between this and the length between this, and try to compare those lengths and see which one is smaller. So we said, oh, what if we minimize, if this is the vector representing the distance between what we receive and what we transmitted or possibly transmitted, we look at the norm. What we realized is that this term can be broken into some other terms. We did some linear algebra there, and we showed, oh, it depends on the norm of R, which is fixed, it doesn't change. It also depends on the norm of these SIs, which are the signals, 1, 1 or 1 minus 1 that we're transmitting, but since we know what we transmit, we can design those signals. We design them to have the same norm, so that doesn't change with really I. They're all just equal to 2. And then it depends on the inner product between R and SI. And then we said, well, if we want to minimize this, and this is with a negative sign, then if this value is maximized, then this is minimized. So maximizing the inner product will minimize the error measure. So we want to find which one, is it 1 or 2, that has the maximum value here. If, let's say, 1 is the right one, then that would also minimize this component. So that's what we did last time. And the classification procedure that we developed was the following. If we only have 2 signals, we say, oh, let's do, for each one of these indices, 1 or 2, we compute the inner product between what we received and what we sent, what's possibly was sent, sorry, the possibilities. And then in one case, the inner product with R with S1 was minus 0.17, and with R2, with S2, it was 2.03. And then, oh, wow, which one is maximized? For which I, the value is the maximum? This one, right? Yeah. So then the signature comes actually from satellite 2. So we return the index that maximizes the above, hence we return the index 2. This is a classification problem, right? We say, is it 1 or is it 2? We do the inner product, comes down to be 2, we return 2. Classified. Okay? Any questions? That was kind of an overview, just because how long it. Yeah. Classification signals. Well, we know, well, they are specially designed because we know what is the signal that is being sent by the satellites. We get something that we receive, and we want to find which one is it. We don't know. Another classification problem could be, oh, here's a picture of me, here's a picture of Anna. You tell me which one is Anna, which one is me. That's a classification problem. Or is it a dog? Is it a, is there a dog in the photo or something like that? Okay, so we return I equal to. Now, again, we want localization. So satellites transmit this unique code. Each satellite will have a unique code. For example, or this satellite will have right? Because it's like a -1. And this is this is okay? And then the signal is received and being digitized by the receiver. And the 2 problems that we have is, well, all satellites transmit same frequency, so they could potentially interfere with each other, right? 2 signals are being, signals are being transmitted, and we're receiving both of them at the same time on the same channel. That can be a problem. And then the other one is that we really need to figure out how long it took from the signal from each satellite to be received. And so that's the timing problem, which we're going to talk just immediately after. Okay? Okay, so first of all, we want to solve this interference problem. So how do we solve the interference problem? What is interference even? Okay? You're receiving some signal. Okay? What are the possibilities when you have a 2-satellite system? Think about it. What's the possibility of my signal being? I received some signal. What are the possibilities?
It could be that you received a signal from the first satellite, you received a signal from the second satellite, or you received the combination of the signals from both of them.
So either S1 is transmitting, or S2 is transmitting, or S1 and S2 are transmitting.
Or none.
Or none. 4 option. 4-way classification problem. Okay? 1, 2, 1 and 2, or none. Right? 4-way classification problem. That's what we want to solve. And what we want to actually is figure out which codes or what type of signatures these satellites should be transmitting such that we will be able to determine that classification problem. Right? We're designers, And so maybe there are good codes and maybe there are worse codes to do that. Let's say satellite 1 was going, oh, oh, and satellite 2 was going, oh, oh. That would have been a problem because it's the same code. So obviously we want to have different codes. Okay? But how different? Let's think about that. So possibilities are that either both sats are transmitting. In that case, the signal that we are receiving is S1 plus S2 plus some noise. Okay? Could be, right? Some noise. There's always noise. Noise is always. There's no noiseless signal. Okay? It's always noise. So we're receiving that. The other option is only S1 is transmitting. And in that case, we will receive R would be equal S1 plus noise without the S2. Third option, we're receiving so only S2 is transmitting, and then we'll receive, in this case, we'll receive S2 plus noise. Or possibility 4, quiet, no satellites above us. In that case, none of the satellites are in transmit, and so we're receiving just noise. And we need to figure that out. Okay. So how do we go about it? Okay. So let's just look at possibility 1. Yeah.
If you measure like noise with neither satellite on, will that noise be the same noise for any of the other situations as well?
Is noise the same all the time?
I wouldn't think so.
Is that what you're asking?
Yeah, because we're using the same N for all of them, so is it the same noise?
No, N is kind of like representative.
Oh, so it could be, it's different for all.
It's every instance, it will be different. And if it's a vector N, it will be different for every entry. And it would often have a Gaussian or a normal distribution, but not always. For those who don't know what a normal distribution is, the likelihood of being more zero, it's kind of like a bell shape. So you're more likely to have something that's close to 0 as opposed to having something, high or very, very in negative. And typical random processes like coming from thermal noise are, they have this statistics. But it doesn't have to be that. But we assume that it's always different. We also assume that the noise level is a certain level, but we always, our signal to noise ratio needs to be high enough so we'll be able to detect. If the noise is just, Anna, can you go like shh?
Really? That loud?
Yeah. No, keep going for a long time.
Oh,
If the noise is too high, then you can't hear anything, Right? If the signal to noise ratio is not good enough, then it's very hard to hear. Does that make sense? Right? So it's always we're relying on the fact that, even in this room, there's noise, right? Like if we're just like try to be quiet, but we're never quiet, there's always noise. But I can speak above that. Okay, that means that signal to noise ratio is high. Thank you. Good point. Okay, so in that case, both are NTX. And we want to know which satellite is transmitting, right? Okay, so what would you do? Which one is transmitting? Or like what situation is? What would you do? A linear, no, I just have R. I don't, I know what S1 is, I know what S2 is, but I just received R, and it's just 2 numbers. And I want to know which of the possibilities happened. What do I do? Gaussian elimination. Well, I know S1S, possible. Yeah, actually you could do some fitting, but we learned something a little bit simpler. Maybe some other possible. You can do a fit there. That's a possibility. You might have a problem with that because you have one equation and then two unknowns, right? So it could be a problem, right? So that might be an issue.
Couldn't you just find the dot product or the inner products?
The
and find the
inner
correlation?
product. How about we try to see if it matches, right? We know R is a vector. We know S1 is a vector. Let's try to see if they're close, right? If they're close to each other. If R is close to S1, R is close to S2. Let's look at all the possibilities. Okay, so what I'm going to do is I'm going to do an inner product with S1. See what happens. Okay? We're going to do, this is a bracket. Remember bra and kets? Remember that? Turns out it's also in physics. It's so hilarious. Bra, which is a column vector, a row vector, and then kets, which are row vectors, and it's a bracket in a product. Funny, right? No? It's kind of funny. I mean, brackets, come on, okay, whatever. I find this hilarious. Every time I hear it, it's just... Okay, so we do this inner product. Let's try to figure out what this inner product means. Well, I know what R is. R is this, right? Could be. I don't know what it is, but it could be this. So let's see, theoretically, if this was the case, what would happen? Okay, what would happen is that this is R. So I got an inner product between S1 plus S2 plus noise with S1. Now, inner products are linear, so we can open those brackets, right, and expand those coefficient by taking an inner product S1 with S1, S2 with S1, and then the noise with S1, right? So S1 is inner product with S1, and then S2 with S1, and then the noise with S1. Okay, so that would have been if, no matter what the case is. And the question is this on, is this off? I don't know. I mean, but let's try to understand how these entries affect our inner product. Okay, let me argue that this one is going to be small. If the noise is not small, we got a problem. Okay? We got a problem because our signal-to-noise ratio, we're not operating at a good regime. Then we need to bump up our signal or get a better antenna or an amplifier or something. But, that has to be relatively small. So we'll just assume that this is a small value. The inner product of noise with S1 is small all the time. Okay? All right, that's small. Okay. Now, the inner product with S1, that's a desired one. We want to make sure that this one actually has the value, right? Like if we're close to if S1 was transmitting, that's going to give us a value, and we know what it is. It's 2. Okay, S1 with S1, it's 2, because that's the inner product of the signal with itself. Great. That's really what we want. That's the desired one. But if S2 was also transmitting at the same time, we still want to be able to detect that, right? We want to be able to detect that. But we don't want the signal from S2 to mess up with our interpretation of S1. That is called interference. Now, what does it actually mean? Well, it means that if there is a word that I'm trying to understand, okay, let's think about who uses like Siri or Hey Google and all that, Alexa and all that kind of stuff, right? Have you ever talked to these systems? And then you tell them, let's say, Hey Siri.
I'm sorry, I can't understand.
I'm sorry. And then you tell them a word, right? You tell those systems a word, and then often they identify it. You know what they're doing?
Here's what I found on the web.
They're doing cross correlations with some signatures of your voice with whatever database that they have. That's what it's doing. And then deciding if that's what you said or not. Okay, which word among all possible words, right? That's one implementation that it's possible to do. Now, sometimes there is a mistake. What does it mean, a mistake? A mistake means that you said one word and it was identified as another. So the situation here, if S2 inner product with S1 would have some value, and let's say S1 was not transmitted, like the satellite 1 didn't transmit, we may mistake S2 as being S1 because we're doing inner product with S1. Sorry, satellite 2 being S1. We may mistake them. Does that make sense? Let me just repeat myself so I get a coherent sentence. Okay. Let's say we're checking if S1 transmitted. We're doing an inner product with S1. However, satellite 1 did not transmit. Only satellite 2 transmitted. But if there is a component, like if you actually have some similarity between S2 and S1 through this inner product, if that has some value, we may mistake that S1 actually transmitted even though it's S2. Does that make sense? That is called interference. And that's why Siri or Google or Alexa or all whatever voice-activated things may have a mistake because they do this comparison and then for some reason there was a fluke and because of interference and then they figure out something else. Okay? So that's interference. We want the interference to be small. So we're designers of code. It's not words, right? That's the good thing about it. It's like, because, you know, a bud and a dud and a chud, and you know, they may look similar, but we can design codes to be very different. And the question is, what code should we design such this component will be the smallest possible? Do you want to repeat that?
Well, you'd want your signals to be, orthogonal.
Orthogonal.
Yeah.
If the signals are orthogonal, what's the inner product between orthogonal vectors? 0. So then the interference will be 0. So if we design the codes to be orthogonal, the interference will be 0. And that's a good thing. Okay? All right. So we're going to make them orthogonal. So if we design S2 and S1 to have an inner product of 0, either basically orthogonal, then we're in a good situation. Okay, here's an example of a decoding. Let's say we receive this signal. And we know that the codes are 1, 1, 1 and 1 minus 1, and that's the noise. Okay? That's what we received. And we want to classify this. What do? Well, we do this. We take R1 inner product with S1. So 2.01 minus 0.03 times, inner product with 1, 1. What is that equal to? Like this, like that. It's one value. 2.01 minus 1.98. Thank you. So 1.98. And then we do an inner product with the other. So 2.01 comma minus 0.03, 1 minus 1. That equals 2. $2.04. Yeah? 2.04. What do we conclude from that? What would we conclude? Yeah. Both have been active. Both have been active, and it kind of makes sense, because if I've got like kind of a 2 and a 0, right? What is a 2 and 0? Well, if you add those two signals together, 1, 1 and 1 minus 1, you get a 2 and a 0, right? That's the closest thing, right? So both of them will have some value, right? So in that case, both S1 and S2 transmitted. Okay, that's how we classify. And what about R2? Do the inner product right now in your head. And what's the inner product with S1? What's the inner product with S1? Negative 0.02, right? Yeah, negative 0.02. And what's the inner product with S2? 2.04. So, negative 0.02 or 2.04, which one is higher? 2.04. Hence, it was S2. And does it make sense? Well, obviously, this looks much similar to 1 minus 1 than it is to 1, 1. Does that make sense? Okay. So that's the procedure that we do for detection. Now, what do actually satellites, GPS satellites transmit? They use what's called gold codes, is these type of codes that try to make, that are about 1024 symbols long. And they're orthogonal to each other, or slightly orthogonal to each other, very close to be orthogonal to each other. And basically have those properties. They're chosen by this property of being orthogonal to each other. And these are examples of 3 gold codes. There's a series of 1 and minus 1s, but 1,024 of them. Okay? Right? Yeah. Instead of R being 2 by 1, it is 1024 by 1. Okay? It's a vector that's very, very long. Yeah? Oh, how do we know we're reading the start and cutting and like timing? Basically, you're asking about timing when we receive it, right? Well, right now we're ignoring the timing. We're assuming that we just receive, exactly when it's transmitted, right? We said timing later, and we'll just get to that in a second. Okay, these are examples, and let's say we received this signal. Which of the 24 satellites have transmitted? Just stare at this, tell me. It'll take a while, right? Well, it takes a while when looking, but obviously we have our tools. I mean, computer, doing inner product between 1024 and 1020, I mean, it's just nothing. Like, it's just like you don't even, I mean, it's just like maybe a few cycles. And cycles are at gigahertz, right? So it just doesn't take long to compute those. And so what would we do in order to figure out? Well, we'll take an inner product, each one of the codes that we know, and see which one is high and which one is low. Okay? And then based on that, we would assume that we get some satellites are transmitted. So what we're going to do is we take R and take an inner product with SI. SI is one of those 24 possibilities, which is also R transpose times SI. And we have to do it for S1 and S2 and S3 and S4. So like this and like that with S1, like this and like that with S2, like this and like that with S3. Wait, that sounds like vector matrix multiplication. That sounds like this with S1, like this with S2, like this with... Does it sound like matrix vector multiplication? Because it is. When you have vector matrix or matrix vector multiplication, effectively you're performing inner product. Did you know that? That's what you're doing. That's matrix vector multiplication, vector matrix multiplication. They're all inner products, either with the columns or the rows of the matrix. That's what they are. Okay, so what I could do is, how about I create a matrix that its columns are S1, S2, S3, all the way to S24. And I take this R, transpose, and then multiplying by that matrix and do like this, like that. Do I get the result that I want? Exactly. The first element of the row vector that I'm going to get at the end is going to be the first inner product with with the signal 1. And then the last one would be the one with satellite 24. So I can just do that. And I will get a row vector that is R transpose S1, R transpose S2, and all the way to R transpose S24. That's pretty awesome. Now I get a vector. You know what? Vectors I can display. I can plot that as a graph, right? And then let's see what happens. This is the graph. This is entry 1, 2, 3, 4, 5, 6, 7, all the way to 24 of this vector that I just computed. What do you see? You see some spikes, and you see some signals that you see some values that are really, really small, and some that are really, really high. What does that mean? Did satellite 1 transmit? Why? Because the inner product with the signature was close to 0, so it's probably just noise, right? There's nothing there. Okay. What about satellite 2? Same thing. Satellite 3. Likely, because satellite 3, whoa, suddenly there's a large value. Okay, and so on and so forth. So maybe satellite 15. What about satellite 17? Yeah. So right now, we know the size of the signal that comes out. The size of the signal that comes out is between 1 and -1. That's what we receive, and that's what it is. There's no amplitude there, depending on how you send it. Okay, there's some subtleties in how you send it, but the values that you get are binary, and you compare binary signals. Okay, but you're right. If you have a problem, like if you have difference in amplitude, well then I cannot ignore the SI, the norm of SI that I ignored before. Right now, we're assuming all of them are the same. Okay. Okay. So what I'm going to do, yeah. What do you mean?
We're assuming each satellite transmits a binary value. We receive each signal with the same amplitude. But if a satellite's like further away,
okay, so you're talking about the amplitude of the signal that's being sent, and that's something slightly different. Okay. The way that we detect it. So we're not actually there's a detection methods that are ambivalent to the magnitude that is being sent. It's either you detect it or not. But once you detect it, then you get those values. And I'll explain a little bit later what it means, but it's a little bit tough to kind of go over it. But I'll just give you maybe a hint, maybe that will solve your issue. But in this case, when I did those inner products, just simplified problem, what do I do? How do I decide which one was transmitting? Well, what is large? I mean, like what is small, right? Like I need to decide on a threshold. Can you build a comparator to do that in hardware? Yeah, you could potentially.
Yes.
You could also do that in software, right?
Yes.
That's an if or greater than, stuff like that. And you decide on a threshold. What threshold should I choose? Is that good enough? Is that good enough? Is this good enough? All of them look fine for this level of noise. What if I had more noise? Oh yeah, up the threshold, right? Right. So I'll put the threshold like somewhere here, right? That guarantees, right? But remember, when you have noise, something like this, then actually those peaks will also fluctuate a little bit up and down. So depending where my threshold is, it's kind of like either I detect too much, false detection, if I set the threshold too low, or if I set it too high, I might have misdetections because my signal may come down, right? So maybe there's an optimal one based on some statistics and the noise level that I can come up with. And for that, you need to learn statistics to find the optimal threshold from a statistical point of view. So CS70, 126, all these classes teach you how to choose that. Yeah. No, not in this case. The question was, is there the matrix multiplication to reduce noise? You can reduce maybe by the code, by the length of the code. There's all sorts of stuff that you can do, but not by the matrix multiplication. Okay, so the satellite that we picked are 3, 15, and 17. Now we're getting into the timing. Okay, so I'm gonna adjust a little bit what I'm saying. Satellites transmit. They don't transmit a unique code. They actually transmit what's called a modulated code. It's a radio signal. Okay, it's a radio signal. It's a radio signal that sounds like boop, boop.
Boop, boop.
Yeah. All sorts of stuff like that. Anyway, pay attention.
I was looking really hard to understand what you wanted me to do. Which noise were you expecting this time?
Some noise too. Anyway, we're receiving a modulated signal. What does it mean, a modulated signal? Well, the satellite transmitted about 1.4 gigahertz. That's the frequency of GPS. And the signal that they transmit is actually, it's modulated. So there is this carrier that changes the electromagnetic waves at, like the electromagnetic field changes at, billion times a second, gigahertz, right? So billion times a second it changes, but we carry information at a slower rate, so we overlay our information on top of that radio wave that it carries it. This is called modulation. And there are many ways to modulate an RF wave. One example, if I wanted to send 1, 1, 1, minus 1, and 1, I could do what's called amplitude modulation and send a constant amplitude for a certain period and then the same constant amplitude for the same period, another period, same amplitude, and when I want to transmit the minus 1, I dip the magnitude a little bit. So it's all relative to each other. And that would represent then a minus 1. And then after that, I go back up in amplitude, and that represents a 1. So when you ask about the signal, it's like I'm receiving 1, 1, 1, like maybe it's a weaker 1. No, because here it's either the same amplitude and then lower 1, so then I can decode a 0, and then I get a 1. So that's one way. Or you can say, oh, how about I change other components? Let's say phase. What does it mean changing phase? I transmit a cosine for a certain amount of time. I transmit a cosine for a certain amount of time, a cosine for a certain amount of time, and then I flip the sign of the cosine when I want to represent a 0. So I flip it by minus 1. So you see there's a change here in the phase of the signal. That's called phase modulation. I can also do frequency modulation, changing the frequency when I want to transmit a 1 or a 0. Okay? So these are the options. And this is effectively how it's done. The receiver demodulates and gets the bits. And then you can do cross correlations and stuff like that. Okay? So signal is received, demodulated, digitized by the receiver, and then you could do stuff. You heard that? That's taking a 1024 long gold code, slowing it down to the range where you can actually hear it, and that's kind of how it sounds when you change the sign of a cosine. Very fast. Okay? Like a modem. It sounds like a modem, like an old modem. Because it is a modem. All right? That's how Wi-Fi sounds if you slow it by about a million times. Okay? All right. So the problem now are timing. Somebody said, it was like, how do you know if you get the beginning or the end or like, or the signal? Maybe I missed it. I don't know. Maybe it's too late. Okay. So this is what we sent. This is a satellite sending this. And this is what's received. So how long did it take the signal to come? Well, actually, the signal is received is this thing. And then we sample it, we digitize it, so we get those values. We get like, small, 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 and then kind of like, something higher, 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 negative, and stuff like that. And the question is, okay, well, how long did it take to get to us? That was transmitted, that was received. has an idea? Yeah? 3 samples. It took 3 samples delay. There was this 3-sample delay between what we thought that the thing is, like we started recording, and then when we know we time synchronize, right? So we assume that you're also carrying an atomic clock with you, okay? Just assume. And so you're time synchronized with the satellites. We'll solve that problem when you were not carrying an atomic clock afterwards. But let's say we're carrying an atomic clock. We know when the satellite's transmitting, and then we are starting to record when the satellite's transmitting, and then this is what we measure. And we see, oh, it's like, 3 samples away. So there's a delay between the start. That's cool. And if we know the delay, and let's say this delay is, 3 samples. We sample, let's say, 1,000 times a second. Let's say that's 3 milliseconds. And if we know the speed of light, which is 300,000 kilometers an hour, we know that this is about 900 kilometers away. Okay, that's how we can find. From those delays, we can find the distance. Okay, now how did you know that it's 3 samples delay? Who said 3 samples delay? You did, right? How did you know? You can kind of see that it shifts up. What did you do with your eyes and brain? How did you know that this actually was a satellite? It's not noise. You don't know? Look at the signature that being sent. Look at whatever. It's similar, right? So you did some matching, pattern matching. And how did you know it started at 3? Can I say that you kind of maybe compared and saw where it matches the best? Okay? Maybe that's what we should do. Kind of like see where it matches the best. And then that would give us the time. Okay? Let's say we're looking for satellite 1, we have its signature, and we'll try to find where it matches the best with all the time shifts. How do you do matching? What is the matching, pattern matching algorithm that we learned? What? Inner product. But we need to do several because we need to find all the shifts. That's what we're going to do. And you know what's called that operation? It's called cross correlation. Okay, so that's exactly what we're going to do. Kind of makes sense now, right? Well, we're about to do that. So we're going to pattern matching some signals. And we're going to develop some mathematical formulation of how it actually is written. So you kind of figure out, like when you see that in literature, you understand. But the idea it will be this inner products of shifted versions of our signature that tries to match the signal that we get. Okay? So this is what we receive. We receive, I think we have 9 samples. And our signature satellite, we know it's 5 samples long. Can you do inner product between a vector in R9 and a vector in R5? Doesn't compute. It doesn't compute. We can't, like this, like, ow! Broke some of my fingers because they don't fit. Can't do like this, like that. So the problem is that the vectors or our signals are not the same length. One, R is in R9 and S is in R5. They don't fit. I can't write it mathematically. I want to write it, but I'm having a hard time. So what's the solution? Pad the vectors by non-information. Okay, let's pad them, and then they can become similar length. And you know what? How much do you want to pad them? I'm going to pad them to infinity. Why not? It's not practical, but it's really nice when you write that as an expression. When you program it, you don't pad it to infinity. But when you write it down mathematically, it's worth writing. It doesn't cost me to write all the way to infinity. I'm just going to pad them to infinity. I'm just going to assume that we're going to define basically an infinite sequences, two infinite sequences, R of n and S of n, by zero padding those signals. And that what it means is that if I have the vector R being composed out of component R0, R1, R2, all the way to R8, and then I'm going to create a new sequence called R of n that between 0 in this index and 8, it's equal to the entries of the vector R, and it's 0 elsewhere. So that's a new sequence, R of n. It's not a vector, it's a sequence. Infinite sequence, actually. But from entries n equals 0 to entry n equal 8, it equals exactly the same values as our vector R. Does that make sense? And I'm going to do the same for S. If S is a vector of size 5, then I'm going to create a new sequence that between entry 0 and 4, it would be the values of S sub n, and there will be 0 elsewhere. Okay? Why? Because it's convenient from a mathematical description point of view. And that's something that you really, it's good to know because you want to communicate some ideas. If you are able to write it in a compact and convenient way, that's also communicating that idea very easily. So here's what we've done, basically. If we have these vectors, now we're just creating two sequences that are just padded. Huh? It's same, but different. It's different. You know, R of n is not exactly vector R. They carry the same information, just a different representation. So this is R of n, and it's the same vector. Now it has like indices, and has infinite one of them. You know that it's 0 here, and it's 0 here, 0 here, 0 here, and the values are right in this case. Okay, so I've done that. So now I want to pattern match them to see if they, when they're this, you know, when they fit, right? So first I kind of add all those zeros where I want to, and now I'm almost ready to do it. Okay? Okay, so now I got these two infinite sequences. Turns out that inner product is defined over also infinite sequences, and it's exactly the same. You can think of it as an infinite vector, okay, that you just multiply those elements of. And I'm just going to compute the inner product between the sequence R of n and S of n. How's the inner product? Well, I just multiply the element and add. Multiply and add. Multiply and add. Multiply. In the same way I would do like this, like that. Okay? That's exactly how we would do it. So I'm going to write an inner product between the sequence Rn and S of n, which is really the sum of n goes to infinity, minus infinity to infinity of those elements. You know, multiply this by this, 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 this by and add. Okay? Does that make sense? And that would be the same, if you think about it, as doing an inner product. Inner product takes the first element, multiply it with the first element, take the second element, multiply with the second element, and then add them together, and so on and so forth. Are you with me?
Yes.
Well, thank you, because your eyes are kind of like a little bit wandering around. Now, here, I want you to pay attention here, because this process I'm going to do, which is cross-correlation, is also very similar to another operation. It's called convolution. Not exactly the same, but it's very similar. You'll see that many times. And I'm sure you maybe heard about convolution. Have you heard about convolution, the operation convolution? Okay, you'll hear a lot about that in many other classes. It's very similar. So the same similar operation is done here. Okay. So what we have here. Well, if I do that, then I multiply this by this, this by this. I mean, I know that these are zeros. So do I need to count n goes from minus infinity all the way to minus 1? Do I need to include those values? Because they were zero padded, so I don't care about that, right? I don't care about the entries n minus 1. I don't care about the entry n minus 2. I don't care about them because I know they're 0. I just padded them. I just put zeros there anyway. Okay? Do I care about n equal 8, n equal 9, n equal 10? No, I padded them too. So really my sum, while it says to be infinite, it's only a sum from n equals 0 to 7. Does that make sense? It's only a sum, because otherwise I've 0 padded them, right? So I know that that sum is the same thing. So now I have a finite sum. It's a finite sum, but now also you can think of it as a, oh wait, I'm actually taking this vector and doing an inner product with this vector. That's the same thing. Okay, so that's how I 0 padded nicely, so you don't even notice that, you know, oh, I added those zeros and where I added them and stuff like that, right? So it's nice. Okay. What is the result of that? Well, the result of that is I effectively take this vector and then compute an inner product with this vector. That's the same thing. So let's do it. This is 0, 0, 0, 1, 1, 1, minus 1, and 1. Right? Inner product with 1, 1, 1, minus 1, 1, and so on and so forth, right? So let me just write that. So I got these two values here. These represent those elements up here. This represent those elements down there. Okay? Look. 1, 1, 1, minus 1, 1. 1, 1, 1, minus 1, 1. 0, 0, 0, 0, 0, 0. Yeah? Okay. Great. Like this, like that. What's the result? You know what's funny? You take a 0, multiply by a 0. Take a 0, multiply by a 0. By a 1, sorry. Take a 0, multiply by a 1. 0, 1, 0, 1. All of these were 0, right? Okay. Then 1 times 1. But you added to it 1 times minus 1. That adds to a 0. Anyway, you keep going. What you see is actually that this inner product becomes 0. Okay? And I can see all of that here. Here, 0. Here, 0. Multiply by this, 0. Multiply by this, minus 1. Multiply by this, 1. Multiply by this, 0. Multiply by this, 0. Multiply by this, 0. So you sum 0 plus 0 plus 0 plus minus 1 plus 1 plus 0 plus 0 plus 0, I get a 0. Oh, I get nothing. Okay, that's cool. I guess that's not the right match. So what do? Okay, it doesn't match when I just try to align that. So what would you do? Shift it, right? Let's shift the signature by 1. Okay? So how do we match with a shifted version? That's really the key. How do we match with a shifted version?
Do we take the inner product of R of n and S of n minus 1?
Right. How do I shift the signal by one sample? I subtract from the index 1. If I subtract in this 1, then for index number 0, I start with minus 1. So it's delayed. Okay? So if I do that, if I compute R of n inner product with S of n minus 1, then I do basically inner product with a shifted signature. Ah, that's cool. And this is what I get. Okay? So now let's do it. So I did this, n with minus 1. So this results in that. And now I look at those inner products, right? And now I can compute that over a finite sequence, right? I don't need to compute it. So actually, let me shift it. This is shifted. Okay, now it's shifted. And now I only need to compute it over a finite number of measurements because otherwise it's 0 padded, right? Okay, so let's do it. This times this, 0. This times this, 0. This times this, 1. This times this, minus 1. This times this, 1. This times this, 0. This times this, 0. So you sum all of that, the result is 1. Still small. Okay, but let's keep going. Let's keep going. We're going to maximize it. Yeah.
So in this case, that thing on the bottom should be labeled as S of n minus 1.
Oh, yeah, that's true. Yeah, S of n minus 1. That's right. Thank you. Yeah. Yeah, bottom that slides the window. Yeah, absolutely. It's taking the bottom and sliding it. One at a time. That's exactly what we're going to do. And we're deriving it mathematically how to write it. Yeah. I can't hear you. I'm sorry.
Okay. Is R of n
Ooh.
a vector, or is it just a
R of n is a sequence that between 0 and 7 has values representing what the vector, the signal, the samples that we received. Okay? All right. Now, here's what I'm going to do, actually. You see this 1 over here? You see this 1? Okay? Before it was a 0. Before we shifted it, now it's a 1. I'm going to call this operation, okay, correlation between R and S at index 1. Can I do that? Why not? Right? When you do that, when I write this, what you do is you effectively, kind of do a pattern matching in your head. Oh, correlation equals the inner product. If you have a 1 here, then I put a 1 here. Right? Like, I can do that. Why not? So that operation, when I say cross correlation R of S at 1, this is the same as shifting S by 1 sample and then computing an inner product with R of N. Okay? That's what it is. Yeah, we're padding because we know, but like from a mathematical point of view, this is when I write the inner product here over infinite sequences, it's just easier to work that way. But effectively, if you do things on a computer, you know what the lengths are, and then you adjust accordingly. Okay, so that's an implementation point of view. But this is more general. Yeah, if we didn't know what the length are, then we just do that. Okay. All right. So now we can do this operations for every shift. We do this operation for every shift. So we computed it for 0. We computed for 1, right? So for 1, it was 1. For 0, it was 0, right? Okay. So now we can just keep going. Keep going. What about 2? Right? Correlation for 2, I shift this by 2 samples, and I compute an inner product. What's the value going to be? Well, let's see. Let's do it one more time. This is 0, 1, 1, minus 1, minus 1, and then 0. What is that? It's a 0. Okay, so they sum to 0. So then I fill, and a 0 here. For 2. For index 2, which is represent the shift, I fill 2. Keep going. Let's do 3. That's 3. What the value is? 5. Okay, I stick in 5 here. That looks pretty high. Remember that we actually identified 3 to be the right one. I'll just keep going, though. We don't know. We don't know yet. Let's keep going. Okay, let's do it for 4. Now it's shifted by 4. We do in a product, we get a 0. We put a 0. Keep going. 5. We get a 1. We get some values. We shift again for 6. We get a 0. That's what we get. We shift again. 7, we get a 1. And we fill it. Now, if I shift one more time by 8, because I know how I zero padded, what am I guaranteed to get? I'm guaranteed to get 0. So I really don't need to continue computing. I know that those are zeros. Okay? What about those two, in the beginning? Also, right? They're not over. Oh, actually, these I can compute still. Actually, let's do the minus 1. What was the minus 1? So I shifted the other way, right? So what's the inner product? In this case, it ended up being actually 0. Just for, no, 1. Actually, 1. Sorry. 1. Okay, so I put a 1 here. And what about minus 2? Is 0. And then you can keep going also in the negative, and then you don't have to, at some point, you don't have to do anymore. Okay, so this is the result of our cross correlation. Now it's a sequence. It's an infinite sequence, but we know that it has values interesting only within a certain region. Okay? And similar to before, that we looked at different codes, now we just looked at shifted code. We can also set a threshold now and say, 3 is the maximum, and that is our delay. That's pretty cool. So we set our threshold, and we say, here's a sequence, correlation of R, of S, as a function of K, looks like that. K star, that's the optimal K, is the one that maximizes this function. What is the K that maximizes that function? 3. So what do I return? I return 3. So that is the result of the cross correlation. I return 3. Now I've got myself a delay. That's pretty nifty. Now you know how to compute a delay using cross correlation. Can you imagine now yourself writing a Python code that has like 2 vectors? You zero pad them a little bit, and then you shift them, and doing the multiplication, do that, and then get another array, and finding where the maximum is in Python. I mean, you can do that, right? You can totally do it. You'll do it in the lab APS. That's exactly what you're going to do. That's why we want you to do the lab, because it's important. There's subtleties, right? We can't do infinite stuff. So you need to remember some things. Okay? So a few things about cross correlation. So if x is of Rn and y is of Rm, then turns out that the length of the cross correlation is n plus m minus 1. All the rest will be zeros, because that's when we do the overlap, that's what would happen. Okay? You can do that drill in your head. Yeah, somebody is like, you can kind of see, but obviously there's some values that outside of it will be 0, right? So it's n plus m minus 1. Where are you from? Where are you from? Oh, nice. Thanks for coming visit Berkeley. This is an engineering class. We have visitors. It's nice to have visitors sometimes.
Tuesday we'll have our own visitors.
What?
On Tuesday we have our own visitors.
Yeah, that's right. Correlation. Okay, the other thing, correlation with x and y and correlation with y and x, not the same. Okay, that's interesting. They don't commute. It's not commuting operations. That's very interesting. Okay, so the correlation is not the same. And then correlation with x with itself is also it's also called autocorrelation. You heard about the word autocorrelation? Probably you heard it, because you heard about correlation before. Oh, do these correlate with each other? Is it correlation or causation? I mean, this is exactly the operation that people are doing. Correlation or causation? Causation. Anyway, a few things about, let me just keep going, because there's a few things I want to cover. So we're consistent also with the recording. Satellites do repeat the codes over and over again. They don't stop. How do they go? So a lot of codes are transmitted all the time continuously. So the cross correlation, in fact, it's not really zero padded then. What we do is we periodically extend instead of zero padding because we're always receiving. So we might actually be measuring, this as the beginning and then keep going, right? So what you have to do with satellites is you have to extend it periodically. And then you extend it with one period before, one period after, and then you perform the cross correlation like that, and then you get the result. Okay, so it's slightly different nuances. This is called a periodic cross correlation. Okay, but instead of basically zero padding, you expand it because this is how the signals are being transmitted continuously. And you can say, oh, this is the delay, and so on and so forth. Okay. Any questions? Yeah, quick.
You said earlier on the previous slide that if at x is a vector in Rn and y is a vector in Rn, then the length of the correlation of x and y is n plus m plus 1. But I thought correlation was just like a number.
No, correlation is not, cross correlation doesn't give you a number. Cross correlation gives you a vector. Or sorry, gives you a sequence, right? So we take our vector, we make sequences out of them, and then do the cross correlation, and we get a signal. Like we get a sequence. And the length of that sequence that is guaranteed not to be zero, or at least it could be non-zero, is n plus m minus 1. And then you pick which index of that cross correlation is the maximum. That's what you return. So the result of a cross correlation is actually a sequence. Okay, it's not. An inner product is one number. But you have many inner product with all the shifts. Okay?
When you said that for autocorrelation, if you do core of x with x, does that always give you the same type of sequence of all ones or all zeros, or does it depend based on what x is?
No, so the autocorrelation of a signal with itself, you do all the shifts. You do all the shifts. Guess when it's going to match? At 0, right? So the highest value is always going to be at 0. And then the other ones will match less. Which leads me to, actually, what are good properties of codes that satellites have? Because now we have the problem of finding both the timing, so we do cross correlations, and also different satellites. Okay? So, here are the issues. 2 satellites are transmitting. We don't know which one is transmitting, whether they're transmitting both at the same time or none of them are transmitting, and so on and so forth. We don't know the timing. We know the codes. So what we could do cross correlation with signature 1, cross correlation with signature 2, right? And then from that, try to figure both the timing and which one was transmitting. Okay? So what are good codes? Okay? So my received signal is S1 of n minus tau, some delay. I don't know what the delay is of S1, of satellite 1, because it's far away. It's, depending on the distance. S2 is transmitting, but it has a different delay. And then I got myself noise. And now I'm going to do cross correlation. Okay? I'm going to cross correlate with S1 of n and see what happens. Okay? So cross correlation of R with S1, that was going to give me a sequence. Okay? It's the inner product between R of n and S1, n minus k, right? That's how we define cross correlation to be. It's a lot of inner product with a shifted S1. Okay? So what is Rn? Well, Rn is composed of S1, delayed S1, and delayed S2. So it's the cross correlation between the delayed S1 and S1, which, if it looks something like that, it would be good. Why it would be good if it looks something like that? What if the cross correlation, the autocorrelation, or like with a signal, delayed signal with itself, would look like that? What would be the problem? because of noise, I might be mistaken to think maybe this is the shift or this is the shift, right? But if it's something look like an impulse, well, then there's no, we were more resilient to noise. We were more resilient to any variation. Okay, so we want that to look like that. And what about S2, shifted S2 with S1? That cross correlation, what we want that to be? That is interference. We only want to look for S1. What do we want the interference to be? Can it be 0? We can make something orthogonal for one shift, but can we make it orthogonal for all possible shifts? Turns out you can't. But you can make it as orthogonal